I'll, sh
Cool.
I'll share my screen.
Cool.
How do you move this? Oh no. I have so many tabs open. Please do not. Okay.
Okay. Hi, we are Tripods. I'm Gizem, and Emma and Amber are going to be in this presentation too. So overview of what are we going to talk about is we will talk about challenge details, system with Spark 1 and system with Trebuchet, and design metrics, justifications, calculations, and next steps. And since we all know the challenge details, we will just go over it. Like it has to shoot about 15 feet from the payload, and it should have maximum 4-inch diameter, 8-inch length, and maximum 2 kilogram. And it has to be safe. It has to be external switch, turn off and on, and it has to be capable of being shot from a rocket, the payload.
Okay, so for our first design idea, we came up with a system that used SparkFun. And so this is just kind of a rough sketch of what we thought it could look like. So we have 2 buttons that will allow the user to receive launching instructions from the LCD display. And then we also have a reset button. And then the LED is there to alert the user when the projectile is ready to be launched. And we also have the adjustable knob, which will specify the spring compression distance. And we're also going to be using the distance sensor to give feedback for measurements and compressing the spring to the user's specified amount. And then the servo will also pull the compressor to the amount specified by the user. Our second idea was a trebuchet system. It's pretty self-explanatory, I think. Yeah, so this sketch is pretty much the basic idea.
Okay, so this was our design matrix. We decided to compare the SparkFun and the trebuchet with the design factors accuracy, which we gave a weight of 3 because one of the main goals was to launch 15 feet, so it has to be pretty accurate. Time to build, which we gave a 1 because while we do have limited time, we could fit it in based on which system we did. So that wasn't as much of like a design factor weighting, I guess. For us, manageable, we gave a 3 because it has to be easily launched for it to work. Well, cost, we gave a 3 because it has to be like within the cost amounts that we were given, which is really important. Securely hold the projectile, we gave it 2 because if the projectile falls out, it won't work. So, and then effectively eject the projectile, we gave it 3 because it must leave the payload to be shot. And whether it's interesting, well, it was important for us like that we enjoyed what we were making. We only gave it a 1 because in our like weighting of which option we chose, we felt like it didn't have as much of a weighting compared to the other stuff. So for the SparkFun kit idea, we gave accuracy a 3 because on the system, it seemed as if, like, based on how we were planning it, you could pull and release from the same spot, and it would generally be around the same accuracy each time. So once you figure out how you would have to shoot it to get into 15 feet, we feel like it would be pretty accurate. For time to build, we gave it a 3 because we are familiar with using SparkFun already from like Cornerstone, so we feel like it would be a decent thing to make and it wouldn't take as much time. For manageable, we gave it a 2 for the same reason. We're familiar with SparkFun, and we feel like with the system that we planned, it'll be easily launched. Cost, we give a 3 because with how we planned it out, it would be within the budget. Securely hold the projectile, we gave it 2 because we would have to figure out a way to secure the projectile. I don't think we finalized that, but we could figure it out. Effectively eject the projectile. 3, same as the last. We'd have to figure out the way to secure it before we effectively ejected it, but I feel like we figured it out. And then interesting, we gave it a 3 because it was our preferred option, just based on like based on how familiar we're with it. And then for the trebuchet, we gave it a 2 because it would be hard to launch to the same distance each time, just the way it's like finicky, the way it was planned. We gave time to build a 1. We feel like it would take much longer to build, actually, because we're not as familiar with that kind of building system. Manageable 3 because it uses simple mechanisms, like as it was shown in the sketch. Within the budget, so we gave cost a 3. Securely hold the projectile 3 because it has like a built-in holder. Effectively eject the projectile would be 2 because it might be hard to get it to leave it the right way each time. And then interesting, gave it a 2 because it was like not as preferred if we were more familiar with the other one. So then in the end, the Spark Fun got the higher score. So yeah, same as I just said, the Spark Fun was more accurate, less time was required, more secure, and we're more familiar with Spark Fun. And honestly, we preferred it because it seemed more interesting too, just because it was less like, it was more with like involved things and stuff. So we did some calculations for the Spark Fun. So for the horizontal component distance, we found, since we're using springs, we would have to use like the force exerted on the spring by the spring on the projectile, F equals negative kx, and the potential energy that's stored when the spring is pulled back must equal the kinetic energy released, that equation. So the projectile launcher will be used to shoot projectiles of different angles. So the components of the velocity vector must be derived to calculate the distance the projectile flies. And since we're only concerned with the horizontal component, that's the only component derived. So we found the equation, horizontal range is the initial velocity squared times the sine of 2 times the launch angle over 2 times acceleration due to gravity. And then you also have to add to that the velocity in the y direction. So we use the final velocity squared equals initial velocity squared plus 2 times the acceleration times the distance for y direction. And then doing all that, we found this equation, which would be the distance that it would go. Yeah.
So our next steps would be more calculations and writing programs for system to function and implementing and testing the system and ensuring it would be secure. Any questions?
All right, cool. Great job, guys. Thank you. Andy, if you want to start with your question.
So I might be missing something. Could you go over how the Spark Fun system would launch the projectile? So like how it would impart this kinetic energy to the projectile? Or is that's along the lines of the projectile holding? Is that what you're talking about there?
It might help if you go back to that slide, the system with Spark Fun slide, if you want to reshare, just so we can look at that while you discuss it.
Yeah, I'll reshare. Yeah, so we were like, kind of like, we haven't like finalized our idea of how it would be held, because like I think just based on like how it would have to like fit with the just in like the requirements, we haven't like definitely planned that. We know that like it has to be, the payload has to be 3.8 around inches and 3.8 inches by 8. It's just how we want to set it up, we haven't finalized, but we know that like it would kind of, I think our initial plan was like to have it in sort of like a tube with like a spring in it, and then it would like on here, this would pull back like the adjustable spring compression knob. It would pull back the spring so that when it's launched, it would be launched from like that tube. It's just we haven't like finalized that or anything, but That's
And then-
our initial
No, okay.
vision, I think.
Cool. So with and then the purpose of the pulling it back with the servo is to make it so that you can sort of have adjustable launch velocities kind of thing.
Yeah. So it would be like you would pull it back, I guess like at a certain angle, a certain distance, so that you could like know where it goes. And then like these things, the sensor and all that would be to make it so it's in the correct orientation. So that's how that would be used. But that's how we think, but we haven't like finalized it or anything like that.
Alrighty.
Cool. Yeah, on that ultrasonic sensor note, I like the way that you guys are thinking. There's might be a possibility of using a different type of sensor that might give you some easier results, like a accelerometer or something like that, where you could sense acceleration due to gravity and which way is down, and then you'd know. So that or a magnetometer would also probably work, but that's probably more complicated than you need.
Is that ultrasonic sensor used to measure the compression of the string or the distance, the spring or the distance to the ground?
I assume distance to the ground because I'm
Okay.
pretty sure like the compression of the spring would be done manually, not through a sensor.
Oh, like you'd press the button until you got it where you want it, kind of thing.
Yeah, I guess so.
Okay.
Kind of, yeah.
Well, you could have like a gauge on there, line it
Mhm.
up like a handwritten gauge kind of thing. I mean, that would work.
Yeah.
It would be simple.
Another thing I just wanted to ask real quick is you refer to this as the SparkFun option. My understanding of that is that it would be making use of a lot of at least the types of equipment that you've used in Cornerstone in the SparkFun kits. Is that the basis of the name there?
Yeah, it's like
happens-
the LCD screen and stuff like that. It's just stuff we've used like in Cornerstone. So
Yeah. The one thing I will say is that we are going to have everyone use the same main board, the Arduino that I sent out. You should be able to, because it's all Arduino based, I think sensors and stuff, as long as you have enough ports, should be compatible. And you could get other things that are similar to the things actually in your Cornerstone kit for the specific stuff that we're using. But I just wanted to let you guys know that.
I mean, you'll be able to run all the SparkFun like sensors and stuff.
Yeah.
Using the Arduino Nano that has been selected. So
Yeah.
I don't think that'll be an issue if you want to go that route.
Yeah, one thing you might have to do differently is they make these things called backpacks for the LCD sensors, which basically take them from having 8 or 10 or however many pins it is that you need to plug into them to make them run, and it's like 2 pins and power and ground. So that might help you guys there if you're running out of pins on the Nano.
Good to know. We are running a little bit low on time, but that's partially our fault for starting late. So I'm going to give you guys a couple more minutes. I was also wondering, so you mentioned I think you mentioned being able to adjust the launch angle, or based on your calcs. I think I might have gotten that idea. So is the system going to either have its folded up state and its launch state, or does it have an adjustable launch angle that you can use? And well, yeah, we'll start there.
I was thinking of it as being the adjustable launch angle. I think that would be controlled by the but the knob is for the spring compression. But the way I was thinking of it, we definitely have to test out a lot more and see what will work best. But I think adjustable makes more sense than having two different states like that. I don't know.
Yeah, so the only reason I ask is because your target is the same. Your target's 15 feet. To save yourself some simplicity, it might end up working so that you only need to have one launch angle that you end up using. And I guess that kind of extends to the spring compression as well. That could be something that you kind of determine, there's a not compressed state, and that so it's not pulled back, and then there's the pulled back state when it's ready to go. And you might not need to have it be editable. I don't know. That's up to you guys, and if you end up building that into the system. But that's just one thing to consider is you might be able to simplify things by reducing some of those variables because the target is the same distance away every time.
Yeah, even if it's not if you can adjust one of those but not the other, assuming infinite power or infinite energy stored in your mechanism or whatever, or infinite, like the potential to store infinite energy, like of course they're physical constraints, but we're not worried about those right now, right? So just adjusting the launch angle could get you pretty much any distance you want, or just adjusting how far you pull back the spring could get you that as well for a given launch angle, right? So you could think of in terms of maybe trying to eliminate one of those systems, right? If you don't have, it might be a lot easier to build if you don't have to both angle the thing and adjust how far back you pull the spring. But that's just something to think about. And given that you don't necessarily know exactly what orientation the thing will land in, I don't know if you've thought about that. But if you don't, then maybe there's more reason to be able to angle the launcher. I don't know, but.
Cool. I don't think I have any other major questions that we can discuss right now. If anyone else had anything pressing, then we can ask that, or if not, we will be good.
Yeah, I had something, but I lost it.
This is why we have a note stock, Adam.
It was like a fleeting thought. I never really captured it.
Alrighty. Well, if that is the case, thank you guys for presenting to us. You guys have some interesting ideas. I'm excited to see what you guys end up coming up with in the spring. So we didn't have much time to discuss feedback and stuff. That's fine. You guys can talk with Bryce and Peyton after. So yeah, thank you guys for presenting to us. Appreciate it.
Thank you.
Thank you.
Good job.
We can hop back into the other call. Yeah.
Cool. All right.
Oh, they're leaving, so we can discuss. Okay.
Well, technically, I'm supposed to let Emma and Holly in starting now, but so they're going back because now we have another group coming. Is my point. But yeah, we can talk for a minute. I'm gonna post a message in their other chat to just let them know. Go ahead.
Yeah. I don't know what this distance sensor was. I thought that was the ultrasonic, but on slide 4, so the distance sensor gives feedback for the measurement and compressing the spring to a user specified amount. I thought that was the ultrasonic, but then when I mentioned that, they didn't respond at all to that.
Yeah. Yeah, distance sensor.
I don't know. If that's what they were using it for, I was gonna say they should use like a linear resistor or like linear potentiometer or something.
Some of my main feedback is like they have a lot of variability planned and they really don't need it. Like, don't make it so complicated. Like, honest to God, fixed angle, fixed spring compression, like,
and preload it.
Preload that shit. And you don't need an LCD screen, I promise. It's fun, but it's not necessary. So yeah.
I mean, they'll figure it out. They'll learn.
It's kind of funny that they thought they were going for, simple and easy to build.
And I'm like, oh my God, this is so. I mean, it's a relatively simple concept, but then when you add in all the other stuff, it's like, guys, that shit adds up.
And
I guess one thing putting a trebuchet in, it's definitely easier to build. It's gonna be more reliable.
Yes.
I was going to mention that they had their drawn so that it was a 3.8 inch by 3.8 inch square peg in a round hole.
Yeah. 3.8 inch square is not going to do it.
They actually have it's
that's about the
3.9 inches is the inner diameter of
3.9 is ID. Okay, yeah. I think they just
Obviously, there
assumed
needs to be
4.
some clearance there too. So
Yeah, plus clearance.
Yeah,
That'll sort of
inscribed
depend.
shapes are hard.
Yeah. Oh, I know. Of all people, I know. Alrighty, cool. I think I'm gonna. If you guys are good, I think I'm gonna let Emma and Holly in. We can continue to jot stuff down when we think of it, but I got to keep this moving.
No, definitely.
All right, cool.
This is
But
apple pie lads.
This is Apple Pie Lads, but none of the people that named it that. This is literally just Holly. So it's a 5-person team, and she's pretty much hard solo carried for the last month. She's very good though.
Wow.
There's only one, but she's good. So, all right, I'm gonna let him in.
All right.
Hi guys,
Hello.
how's it going?
Hi.
Sorry, we're already behind schedule. I thought maybe on the first presentation we'd stay on track, but silly me.
Okay, I don't think I will go over time. So do you want me to share my screen?
Yes, please. Yep. Let me know when you're gonna start, because I'll start the timer. It's not like a hard thing. I just am tracking how much time stuff's going for. And I will just start real quick by recognizing the fact that you have been doing this solo for a little bit, and I will try to fix that for this spring and give you people to work with.
It's all right. It was just this week and last week that I was alone.
Okay. Yeah, this was not the intent, but it's kind of what happened to some groups. So
I don't know. You could have put your name on there like several times, like Holly Lewis. You know, with PI Holly Lewis.
All right, I'm ready whenever you are.
Alrighty, sounds good. We're ready. Go ahead.
Okay, so a little information about the challenge. Our goal is to build a lander that will be ejected from an intro airframe rocket that then shoots a projectile as close to 15 feet as possible. There are a few constraints as to the size. It needs to weigh less than 2 kilograms, have a length less than 8 inches, and a diameter slightly under 4 inches. It also needs to have interfaces for the rocket payload adapter, a parachute attachment, shock cord pass-through, and standard battery/electronics. There also need to be external buttons and switches for power and projectile release. We also realized that in order to maximize our points, we want to land in a launch orientation, have a successful shot of our projectile, keep our projectile mass as close to 200 grams as possible, and shoot our projectile accurately as close to 15 feet as possible. So with this project in mind, our group came together to determine our needs, wants, and nice-to-haves for our lander. We decided we needed it to exit the rocket smoothly, land in a shooting orientation, so either land upright or be able to shoot from multiple orientations, survive impact and launch forces, so be able to shoot after it lands, contain the projectile during launch, release the projectile, and be easily assembled and serviced. We wanted to be able to change the lander's orientation after landing and have some sort of mechanism to dampen the landing forces. And then it would be nice to have a system that senses failure or status, detects ground impact, is able to adjust launch distance on the fly, or relaunch the projectile. Our goals for the projectile, we needed it to be accurately sent within 5 feet, so 10 to 20 feet, and land without significant bouncing or rolling, which affected the material and shape of the projectile that we want. We wanted it to be accurately sent within 2 feet, so 13 to 17 feet, which is an ambitious goal. We also wanted it to be wind resistant, so that also affects the weight and the shape. And we wanted it to be as close to 200 grams as possible so we could maximize our points. So with this in mind, we started designing. One of our designs was the catapult. So in the picture on the right, you can see a basic catapult design. We would have a servo release the latch, which is labeled as the restraining rope on that top right picture. Then the spring contracts and launches the projectile. Some pros about this design is that it's really fun. Just the idea of building a catapult is kind of exciting and a little bit crazy, and there's a lot to learn here. It's not a system that many of us, even those who have experience with maybe robotics in high school, are familiar with. Cons is that it's a little imprecise. It takes a lot of finessing with the spring and the tension and all of the wind conditions to make it accurate within our goal of 5 feet. And it's potentially unreliable when you have that sort of like stored energy in the spring. If it's positioned the wrong way, there's just a few ways it can go wrong. Our next idea was this wheel launcher. So in this design, pressure from a spinning wheel and a guide launch a projectile, or alternatively, you could have 2 wheels spinning opposite directions to also launch a projectile. It can be driven by a single motor, which means that it's easy to control. The cons are that it requires fine-tuning the angle and motor speed to get it to launch accurately, and it must be precisely built, or else the projectile could go in a wrong direction, or there won't be enough tension or pressure between the projectile and the wheel and the guide, so then it won't receive all of the momentum that it's intended to. Another con that's not mentioned here is that this is a design that some of our team members have worked with before, so it's a little, there's a little less to learn here. The third design is a telescoping arm, in which a long arm extends out of the launcher to push or place the projectile. It's driven by 1 or 2 motors connected to a pulley system, as seen in that top picture on the left. Some pros are that it's easy to control, again, just because it's driven by a single motor, and precise placement is a little easier because instead of throwing something or launching something, you're pushing it a certain distance. So there's less effect of outside wind or any other conditions. Some cons is that it's very difficult to fit a 15-foot long arm within an 8-inch restraint. So that would have taken a lot of finessing. And there are a lot of failure points. As you can see on that top photo, those 3 X's represent static points where the string is connected to one point, and then those circles are pulleys. And if any one of those pieces isn't working correctly, or if one of the static points disconnects, then that section of the arm won't be able to extend, and it affects the entire arm. Also, if the string doesn't spool up correctly when you're extending it, when you go to retract it, it can get caught, and then it won't unspool and allow the arm to come fully in. And then your distance would be measured from that furthest point on the arm, making it a lot closer than the 15 feet that we want. The final design is our tape measure design. This is kind of based off of a handheld automatic tape measure in which the user pushes a button and the tape measure has a tiny motor inside it that spins and unfurls the tape measure. And then with the push of another button, it'll retract the tape measure back in. So you can see in the drawing on the left that this is essentially that same design, but within the lander. So as the motor spins forward, the tape measure would extend and push out the projectile, and as the motor spins backward, the tape measure would retract back into the lander. Some pros is that it's creative, and there's something inherently fun and exciting about building something that no one else is building, or thinking of an idea that no one else has thought of. It's easy to control, again, because it's a single motor. It's inexpensive. You can even buy one of these automatic tape measures for like $20, and you can get a regular tape measure anywhere easily for $10. One of the cons is that it's possibly flimsy. We would have to figure out if it's possible for just the tape measure itself to extend 15 feet and stay rigid enough to push the projectile as far as we needed it to. And we thought about a few different ways to kind of make it stronger. For example, like layering 2 tape measures on top of each other, or having 2 kind of Velcro as they unfurled. So with all of these designs in mind, we made our decision matrix. We decided to evaluate our designs with the goals of learning, robustness, ease of control, team building, achievability, and whether it's interesting and fun. So we gave them all weights from 0.1 to 0.3, and we rated all of our designs in each of those categories on a scale of 1 to 5. When we summed them up, we had two kind of clear winners, this idea of a long arm that pushes the projectile, or a catapult. With these two, we evaluated them on a further level. So we first wrote a short description, as you can see in the brainstorm row, and then we decided to think more details. What more information do we need? So for example, for the long arm, how would it be driven? As I said earlier, it would probably be driven by a single or double motor. We then looked at what are the failure points? Which pieces do we need to make sure to make robust enough, make last all the way through? And then what are the sticky points? What's the real trick to getting this design to work? So again, for the long arm, it was how do we fit 15 feet of material within this 8-inch space? Moving forward, our favorite design idea was the tape measure. We want to meet in person to prototype, create some preliminary CAD models, which have already been started as of last meeting, and get a little more excited. Obviously, it's just me here today, but I would like to work with more people in the future. And even myself, like it would be nice to have other people to motivate me to get to the meetings too. And that's all.
Great, thank you. Also, you kept very close to the time. 9 minutes, 44 seconds. Sweet. Alrighty. Does anyone want to start with questions? Adam, I think you had the first one. You're muted.
I'm muted. Okay, that's better. Yeah, I did have the first question, but it's about the catapult. So I don't think we needed to discuss that since they weren't pursuing it.
Okay.
Yes, I will bring up the next one though. 200-gram ball is pretty big for the spinning wheel idea. A baseball is about 150 grams, so whatever you were launching would end up being probably about that weight or a little bit heavier.
Well, in fairness, you can get things that are denser than a baseball.
I know, but I'm saying that it would be 200 grams is heavier than you think. When you're
That's fair.
Flinging something with a spinning wheel.
No one's asked.
It's
I didn't explicitly ban lead, but I don't want people getting lead poisoning.
Launching lead balls sounds like a personal safety and environmental hazard.
Yeah. Did Tyler send everybody lead solder?
No, they actually used unleaded.
Oh, really? Okay.
Yeah.
All right, but back to real questions. I guess. So, I guess for the, actually, I guess we should go in order. What else do we have here? The balls.
Yeah. So on the, if I missed this, totally call me out on that. That's fine. When you were talking about the like long arm idea, did you kind of decide to go away from the telescoping arm in favor of like the tape measure as like a replacement? Okay, cool.
Yes.
I didn't know if those are two ideas or if you like iterated on it to arrive at the tape measure.
Yes, so it started out as the long arm idea was pretty much just the telescoping arm, but then when we got to the decision matrix and we're looking a little closer at this like brainstorming slide where we're describing it in a very short amount of words, that's when the tape measure idea came through. So we were thinking, how could we make a long arm? And then the options were telescoping or coiled. And then that coiled turned into, let's look at automatic tape measures and how would this work?
Cool. Okay, that makes more sense. Thank you.
I have another question about the design matrix while we're kind of discussing that.
I can pull this up.
Yeah, so it looked like the spinning wheel and the catapult were tied. So what made you choose the catapult over the spinning wheel?
We chose the catapult because it just seemed more interesting to us, and that was the deciding factor.
Okay, yeah, that makes sense.
That's fair.
Yeah.
Yeah. I won't tell you we haven't done that.
Adam, I blame you for the parafoil.
So,
I accept responsibility. That was my doing.
I know we're sort of looking at a very high level right now, but did you have any thoughts on how I guess you mentioned you'd power the parachute with some kind of elastic band. That's what you were thinking. Or sorry, not the parachute. The catapult. I don't know where I got that one. Yeah.
So the idea was to have a spring or some other like similar stored energy there, that there's like a latch, or in this case, like in this picture, a rope, and then a servo could release that, and then the spring would contract, catapult would be drawn forward and launch the projectile.
Okay. Yep. And why a spring like that over like a torsional spring or something like that?
Honestly, there wasn't really like a fleshed out decision made about this.
Well, that's all
This
good.
is just
That's,
like pretty much
that's
the
kind of
picture.
answer enough.
Yeah.
Well, you haven't gotten there yet, and that's fine, because I mean you have a bazillion ideas and you can't have them all fleshed out.
Yeah, one question I had is with the tape measures. I'm very intrigued by that idea. That's a creative one. But a question I had is that, have you kind of done any preliminary research into like how stiff normal or even like beefed up tape measures are? Like, is it even remotely reasonable to put it out 15 feet with a 200-gram mass on it and not have it just do that thing where like it like bends?
Yeah. I haven't researched it, but we did talk about possible ways to strengthen it. We had one idea where we had two kind of coming in at a right angle to make it more rigid. And then we also talked about having two that were going opposite directions. So they were spooling out by two motors rotating in opposite directions. So as they came together, they would have Velcro, and they would Velcro together, and that would make it more stable. Does that make sense?
Yeah.
Yeah, I see what you're saying.
Another, I guess I'll throw an idea out there. Are you familiar with e-chains?
No.
You might have
Okay,
heard it
so-
called IGUS chain.
Yeah, I guess chains.
Okay.
They're basically a chain that can rotate about like 90 degrees in one direction between links, and
Mhm.
it's rigidly fixed in the other direction. If that makes sense.
Wait, I think I know what you're talking about.
It is used in FRC
Yeah.
a lot, if that's
So that could potentially
Oh,
give you
yeah.
a stiffer chain than.
Yes, I
than
know
a
what you're
different
talking
geometry.
about.
you might even be able to couple them where like the tape measure is the extending mechanism, but like it's backed by like an e-chainish thing.
Yeah.
I don't know, just spitballing.
Now, would this thing slide along the ground, like push it along the ground? I guess.
Yes, I think the idea is to have a projectile that like can roll or is very low friction against the ground. I think it's just a little overly complicated to have another mechanism that would like drop it and would have to be extended and retracted.
So you'd
So-
like have like
okay.
a guide kind of thing.
Yes.
Oh, I see what you're
Push it.
saying. Okay, yeah, makes sense.
Oh, okay.
I
I didn't pick
yeah.
up on that at first. That's
No, I didn't
that's
either.
smart.
I like that.
Okay.
That's good.
That is very big. So like, I mean, I guess Adam was like, "Oh, baseball's insane, right?" Baseball doesn't sound quite so insane now.
No, if you're pushing it along the ground, it doesn't. If you're
Yes.
launching it through the air with something that's, half a foot long, that's kind of crazy.
No, okay, that's cool. That's pretty cool.
Yeah, that'd be cool.
I guess so. Word of warning, right? You might have to get over some pretty rough terrain, right? It could be in the woods. There could be like a plowed field
It'd be a
or
corn stalk.
corn stalks, like dead
It
corn
could be uphill.
plants.
Could be a bottle of water.
Well, at that point, I don't know that there's any. You can't do anything about
Some
that.
of those are true and some of those are true but also memes. I apologize. Especially the corn stalk. But
But it is a legitimate risk.
but it is true. Yeah. You do want to consider the fact that you are not landing on like concrete. Which helps you in some ways. It's not so bad on your lander when it lands. It's not landing on something insanely hard, but it's dirt. Like it's a field. So it's something to consider. Once we know what launch site we'll be going at, I'll let you guys know and like what the conditions usually like there, because they all kind of have their own feel, and we don't know yet because currently we can launch nowhere. So
St. Albans, you might end up in corn stalks up to your shoulders, depending on the time of year.
just something to think about.
I guess one thing, Scott. So right now it looks like the only plausible launch site is Winnipesaukee, and obviously that's not really going to work for this, right? I don't think.
It could.
You think?
I mean,
Snow?
it depends on how hard packed the snow is, I guess. If it impales itself into like 6 inches of snow, then I bet a lot of these are not going to work. We'll talk about that.
Yeah.
the
Also, just to bring us back to the time.
Sorry,
it's like 9 o'clock.
That's sidetracked.
Yeah, we probably should let you guys go. We will continue to discuss, and when we have feedback at the end, like after today, we'll send feedback to you guys on what we kind of discussed. So, thank you, appreciate it.
Thank you.
Yeah, good
job. All right, yeah, we have to let the next group in soon, but she did a good job. I'm pretty happy with that.
I think we discussed most of our feedback with.
Yeah, we did. I really like the tape measure. I really want to see it.
Yeah, that's cool.
I really do, but I'm really scared of like even just close clipped grass. Just like thinking about rolling a baseball through close clipped grass. I almost think like it's going to be easier if you can make the thing bigger diameter, right?
Yeah,
like
which is so counterintuitive. Everything else wants smaller.
But you can only make it 3.9 inches in diameter is the problem. It's still teeny, right?
Yeah, like for these teams that are doing catapults, like I'm thinking like they want like a ball bearing.
Probably gonna be a baseball.
Just like a big ball bearing, but for her, she wants bigger, which is very interesting.
Yeah.
Different conflicting optimizations.
It is, but still, I'm worried about like just the force required to push a baseball size object through close clipped grass. Even that, I mean, if you think about how fast a baseball gets hit and how slow, how fast it slows down once it starts rolling.
But it doesn't always go to the wall, and it leaves the bat at like 100 miles an hour.
Yeah, so like I'm a little concerned about how she's going to pull that off. But at the same time, I mean, it is a very, very good idea.
Yeah.
Because I mean, really if you can achieve it, I mean, that's going to be like the ultimate repeatability, right?
Oh, it's going to absolutely kick ass if it works.
Yeah.
Yeah. Alrighty. I'm going to let the next guys in.
All right.
Hello, guys. Can you hear us?
Yeah.
Sweet. Sorry, we're a little bit delayed. I should have seen that coming. But I want to make sure that we give you guys the time discussing with you guys. You guys, the groups that have gone so far have had some pretty cool stuff. So I am hoping to give you guys the same. All right. So if you guys do have webcams, if you can turn those on, that would be great. And then whenever you're ready, you can share your presentation, do screen share, and let me know when you're ready to go, and I will stop talking and we can go.
Yeah, I just need to pull up the presentation.
I hate that stupid Google Drive notification that you get like all the time.
Yeah.
Trash settings have changed. I don't care.
Okay.
All right, you try to go?
Yep. So
right.
we're the Chobani yogurts. And next slide. So here's a table of contents, I guess. Next slide. So the challenge details. So a brief summary is we're going to design a payload that lands in the correct orientation after being ejected midair from a rocket. And then once it has landed, it's going to shoot a projectile, which is up to like 200 grams. It's going to shoot it 15 feet away from the payload. And next slide. So the needs, the wants, and the nice to have. So what we thought for the needs was that it has to land on the ground in the intended orientation. Then it has to like shoot the projectile. It has to be able to hold the projectile securely in place. And for the wants, we wanted to safely start the shooting sequence. And it has to shoot a projectile 15 feet. And nice to have would be maybe like a cushion to protect the components of the payload and being able to adjust in case there's like wind or other weather conditions. The initial concepts. So for the payload shell design, we chose to have curved sides so that only the top and the bottom are flat. This makes it so that when it lands, it will always roll onto one of the flat edges. And in the drawing, you can kind of see, I kind of drew it like this, the top two are flat and the sides are curved, and the front view should be curved. Next slide. Okay, and then we talked about a flipping mechanism. So once it lands on either one of the flat sides, we will have a flipping mechanism that will also double as an opening for the launcher to come out. So in the drawing we have, you see the payload with the two motors connecting to the flipping mechanism, and then it should open up from the bottom and then flip it over so that there's an opening, and afterwards there's like a top view of what it should look like. So the motors on the sides with the area where it would open up. And David?
So the initial for our launcher, we decided to use like a torsion spring so that once like the lid opens up, like the shooter will like immediately just pop out. Like we wouldn't need like a motor or something because of the spring. Then we have a string that would fix it so that it would only go up like a certain length, so we can fix the angle. And for the design, we had two different ideas. One design was that we would have like a spring on the bottom of the tube, and then we would just like launch the ball with like a bun or something. The other idea we had was we would have like a sort of like a crossbow mechanism, which is instead of like a spring, we would have like a rope that would extend to the bottom of the projectile and it would launch it forward. And then this is our design matrix. So we ultimately decided to do the compression spring based on this because it just had the highest overall score. We weighted achievability, effectiveness, and stability the most because we thought that like that would affect our chances of that would like maximize the amount of point we get. And then for our calculations, we found that the K value would be 2.21 pounds of force per inch. We had trouble on this initially because we got like varying figures, but Bryce helped us out on this, and we ultimately settled on this value. So our next steps is that we have to finalize our calculations so that we can start to prototype our design, and we have to start finding out specific parts on MechMaster.
Alrighty, thanks guys. So first question I think I have, I think a couple of the other mentors or reviewers have this as well, is so it was a little bit unclear when you were describing your different mechanisms. There seems like there's options for launchers and there's options for like body type of the lander, and I was kind of curious, like, were those independent discussions, or did like certain combinations of them get looked at? Like you mentioned the like flipping to make sure that you're in the right orientation. I wasn't clear if that applied to all of the different launcher types or if that was just like one specific one.
Yeah, they apply to all the launcher types.
Okay, so you want to do that regardless of the launcher. Is that my understanding? Yeah. Okay.
Okay, so the design matrix was done on concept C.
Okay. Cool. I will note with that, and I'm sure Bryce has discussed with you some. We have attempted to do something similar in the club in the past. I will note that it can be a little bit harder than it might sound. So just make sure that you're testing and thinking about the many variables that you can and issues you can run into. I'm having flashbacks.
I'll jump on that train. Yeah, flipping is really hard, especially if you end up on different terrains. Let's say you're uphill, now your force is drastically increased, or maybe you're on snow, so your flipper goes down, but it actually just scoops up a bunch of snow underneath you and doesn't actually flip you over. You might just land on the correct side. So yeah, I would recommend looking into different ways where you could try to avoid flipping, whether that be like mirrored flaps that open so you can actuate up or actuate down to launch your projectile. And yeah, I like the idea of the shell, so you land in a known orientation. But if you could go further with that to avoid having to flip, I think that'll save you a lot of work down the line and a lot of headache.
Yeah, I'll have a slightly less strong take than Adam and say that if you want to flip, it's okay, but just make sure you know what you're getting yourself into is more of the more general cautionary tale, I'll say. But make sure you need to. I think that's generally make sure that it actually gains you something. If it does, okay, but you might not need to. Let's see, what else do we have? I have your presentation up here.
I guess you talked about a crossbow. What were you thinking? Were you thinking like the bow itself would store the potential energy like a real crossbow, or were you thinking it would just be sort of a stretchy bowstring kind of thing there? And like, were you thinking about how would you fit that inside the shell? Like, do you have any details on that, or was that just sort of a general idea that?
It's more like a general idea, but like we were thinking about like something like a rubber band, so that like the string itself would store the energy instead of the crossbow.
Okay, yeah. So that would avoid the need for a long bow, I guess,
yeah.
Which might be difficult to fit in there. Makes sense. What else did we have?
It looks like can you just discuss your decision to go with a string to limit the launcher angle? Did you consider other methods, or was that just kind of like
so like
first idea?
What we thought was like we would have like a mousetrap thing so that it would spring up, and the string would be there to keep it from like going all the way like 180, so it would like keep it at like this maximum angle. So yeah.
So there would still be a force pushing it up, but the string would limit it. The mousetrap is it's just, so you, instead of having a thing move it up to the angle, it's just a latch that allows the mousetrap to go. Okay.
Yeah.
That's interesting. I hadn't thought of that before.
I think the other point with that was that when the flipper actuates open, that's the thing that's keeping it from springing.
Okay. Is it? Oh.
Oh, so there's not actually a latch.
It's very passive.
Okay.
Oh, wow.
Okay.
Well, I mean, you need a latch
not-
for the flippy things, right?
Is that actuating the flipper as well? Or is the flipper
Yeah.
actuating-
So whatever
Okay.
actuates the flipper actually has to be pretty torquey, because not only does it have to potentially flip the rover, but it also has to be able to hold the mousetrap's desire to push the shooter through the flap, or push the flap open using the shooter.
So what happens if you start here, right, and say this size the top, what you want to be the top, right? So a flap comes out and flips it over like this, right, kind of thing. Won't the catapult arm just fling it out sideways like this before it's all the way up?
Yeah, we might need something else to set the catapult thing, I guess.
Yeah, I guess I'm a little confused about how you'd get the flipper to be the exact same thing as the release mechanism. Not that you couldn't find a way of doing it, but
Yeah, another thing I want to note is, do remember that we have the mechanical hard stop requirement. So if your flipper is the thing that is keeping your shooter contained within your lander, then there would need to be a latch that holds the flipper shut mechanically, that you could physically remove when you walked up to it after it landed. Like, you wouldn't have to do anything like electronically with that. It could be just manually removed, but you would need some kind of physical hard stop so that you don't fling open the shooter in flight and like punch a hole through the side of the airframe rockets.
you're not going to do that, I don't think.
Well,
I
what
don't
if you
think
do
it would-
after you've deployed, and then you launch a 200-gram projectile through your parachute.
Scott,
That's possible.
can I ask a follow-up question to that?
Through the whole of the airframe is probably not likely, but it
Yeah.
could jam it in there.
Yeah,
It could
probably
open the
wouldn't
flipper
come out.
enough to hold it. Sorry, go ahead, Bryce.
Yeah.
So the torsion spring is just there to set it to an angle, and then they're still going to have a compression spring that just shoots from there.
Yeah,
The-
no.
They would
Okay,
still be
so
able
the
to have the
projectile-
mechanical stop. They would still need to press a button to
Oh.
make the torsion spring is not a catapult arm. The torsion
Yes.
spring is just an angle to set it, and then they would press a button to then shoot the projectile.
Yes, I do understand that.
Yeah.
But if the motor on the flap were to fail or to go or whatever, then you could arrive in a scenario where the lander is held, like pinned through friction inside of the rocket when it's supposed to come out and do something weird, because the rocket is assuming that the payload falls away, and it would impede the ability of it to do that.
Yeah, I think we need to design the rockets so that they can handle an extra 2.5 kilograms on descent without blowing up. But
Sure.
but yeah, no, that's true.
Yes.
Obviously, you want your payload to come out. So I think I was getting
Yeah.
it wrong though. So as the flipper comes out, the catapult angle thing, well, or like it's not a catapult, but
Yeah, it should still be
the
able to
puncher
flip over.
will come out like this, and then it'll be pointed up like this,
Yeah.
and then it'll go
Okay.
pew or whatever.
Yeah.
Right? Okay, cool.
Yeah.
Cool. No, I just didn't get that. That makes sense.
Okay. And then I guess on the flipping mechanism, do you have an actuation method chosen yet? If not, it's fine. I'm just interested.
No, I don't think we do.
In terms of releasing the puncher or the crossbow or whatever, or just like a servo or something, or any
Yeah.
thought on that? Okay.
I had a question. Oh, shoot. Is this capable of launching from either side, or this cares about which side's down?
I think only from one side.
Okay.
If you've got that passive torsional spring to do the angling, it's going to have to be one side.
Yeah,
right?
that's what I thought.
As far
Yeah.
as I can think.
So is there a way that you're going to like convince the payload to land such that you can be with that side bottom down? I know you have the flippers to kind of coincide a little bit, but if it looks like landed upside down, that would be bad. unless you have a way to fix that.
Well, I think that's what the flipper's for.
That's what the flipper's for, yeah.
Yeah.
The flipper flips it over.
So the geometry of it ensures that it lands on one of the two sides, and then if the top side is down, the flipper will invert it.
Right, but
Not
if
that
the
flipper won't require a lot of torque,
but if that flipper opens, then isn't the shooter going to get in the way of it actually rolling over the right way?
No,
Or-
it shouldn't.
Oh, I guess it wouldn't.
It'll be behind it the whole time.
yeah.
Yeah. And as long as you have a mechanism to prevent the ball from just rolling out.
Yeah.
Okay.
Yeah.
Got it.
And it actually gets around a lot of the issues we had with flipping because it doesn't have to do multiple actuations.
Yeah. To be honest with you, what I was trying to lead you guys to say is we're going to attach the parachute in a place that's going to make it so that it probably lands the right way. But you also had a more robust answer for than that. So if you do both of those things, you'll probably be fine.
Now, obviously, it's nice having a passive angling mechanism, or passive. Obviously, it's spring loaded. But have you considered the possibility of doing something different so that you could have it angle out either side of the payload, depending on which orientation it lands in?
I think we had one idea like that, but it's not in the diagrams, where like basically we'd have something that would set it at an angle and then it just shoot like right through the tube, I guess. I don't know.
Oh, I see what you're saying. Yeah, angle the entire body. Yeah.
Yeah.
Yeah. Also, if you,
I like your shell idea though.
yeah, if you had an active angle thing, then theoretically you could just angle it up or angle it down. Well, it would be turned upside down, but angle it either way.
That's what I was thinking. It would avoid having to flip it if you just have two flat sides and then flaps that are just sort of
they're just
flappy.
covers at that point.
Yeah, they're just covers, and they either
I
one
do
can
like the
fall off.
elegance of how much of yours is passive. I'm not saying like don't do that at all. I'm just we're spitballing.
Yeah. Are we out of time now, or?
Probably.
Good question. I don't know. We got all out of whack. Yeah, that's what you guys.
I believe we started at about 9 o'clock.
Yeah, so technically you guys were supposed to be done 10 minutes ago, but we started to do 10 minutes late or something, so you're good. But yeah, I probably will have us be all set. Cool. Well, I appreciate you guys giving the presentation. Good job, guys. We will send you guys the feedback that we have once we've compiled it. It probably won't be tonight. It'll probably be over the next couple of days. So yeah, thank you.
All right, thank you.
Cool.
Thanks, guys.
Cool.
Should we take a minute before we let the next group in?
Yeah. Rise of Sadafer. Oh my God.
Yeah, if they're going to actuate it with a torsion spring, it kind of work, but I think they're better off putting flaps on each side.
I honest to God can't believe Bryce is allowing this to happen. I can't believe he signed up for Sadafer 2.0. I can't believe it. Like, if some other group came up with that, that's one thing. But him of all people, Bryce, what did you do?
Andy, if you're not intimately familiar with the stories, we'll have to tell you sometime.
No, I'm not intimately familiar.
Oh my God. Here. I'm not sure I've ever hated a creation of mine quite as much as
Me
I
neither,
hate that
and
shit.
I still can't believe I put that on my story.
I still can't either.
It still bothers me.
What was the exact thing you said?
I believe it was "Die in hell, you motherfucker."
I think it was. It's so not like you to do that so publicly.
I was working on like 4 hours of sleep across like 3 days.
Yes.
It was not great. They all came in a car.
Oh my God.
Yeah.
Yeah, we got to the hotel at like 1 a.m. and I thought it was like 4 in the afternoon.
It does seem kind of nightmarish shoving that kind of mechanism in a 4-inch tube.
Well,
they were actuated by Nemo 11s.
That was a bad idea. Anyway, we should probably let the next group in.
Yeah.
But yeah, no, bad. All right, I'm gonna pop into their chat because they didn't actually pop over yet, so they're not in the waiting room. I'll just let them know.
Yeah, never use a stepper smaller than a NEMA 17. It's not worth it. You might think it's worth it, but it's not. Wait, were those NEMA 7s?
No, they were 11s. I'm pretty
They
sure
were
they were 11s.
Okay. With gearboxes on.
The ones that we looked at, like the ones we have for Capstone, look pretty similar. In fact, they might be the same ones now that I think about it.
Just without this gearbox on the front.
Well, we put the gearbox on it.
I know. Well, then I think we bought ones with the gearbox.
No, we ended up doing. Remember, we used those like DC modes. Oh wait, we did buy them with the gearbox, and then even those didn't work.
Yep.
Can you hear me?
Yes, we can.
Yeah.
I don't know. I was thinking about using some really small steppers for a project, but it was going to be a Geneva Drive winch that's like wants to unreal.
Just be
And
wary of the
that's what we
fact
want.
that baby steppers have a lot less torque than you think.
Yeah.
Baby steppers suck.
I don't know.
I think we've all been scarred here.
If you
the
want it
winch
to
I'll
act like
want
a
to
continuous rotation
unreal, but-
servo with discrete steps, then do it. But if you want it to take any load, don't.
You want it to actually be a
continuous
torquey motor.
Little tiny continuous rotation servos are great. You can get a huge amount of torque out of those things.
Way
Yeah,
more than a
they
NEMA
were.
11.
Oh yeah.
Yes.
No, remember when I borrowed your little NEMA 11 after you didn't like it, Scott?
Oh
the
yeah,
same
that's
year.
right.
So I borrowed that for my Cornerstone project, and it brutally failed as well. So then I got like this little rotation servo that's like a quarter the size, and it was incredible overkill. It was awesome.
But those that's pulse width modulation for the speed, not for.
I
mean,
know.
there's no
You can't
position
get the
control
position.
on that thing.
No, there's no
Also,
position control.
I'm
I had to
gonna
come up
step in and say we're already behind schedule.
Alrighty.
we can banter later about our past woes. I'm gonna let you guys actually present because that's why we're actually here.
Right.
Alrighty, I am pulling up your presentation now. Where did my timer thing go?
You guys see my video?
I cannot. But it also doesn't say your videos. It says your video's on, but then it shows a gray screen.
Yeah.
Not sure what's happening right now.
So I believe that you're trying.
I don't know what's going on.
Yeah. Did you join without video?
It shouldn't
No, I
matter.
joined with
but-
video.
Okay. Yeah, sometimes if you join without video, like won't request permission to use it.
Yeah. If you want to leave and come back, like real quick, you can. If you don't
Maybe
care,
I'll
it's
try
also
that.
not a huge deal. It's up to you.
Should I be sharing screen or?
Yes. Well, one of you.
Yeah. Let's see.
Hey, there we go.
There you go.
Nice.
Hello. We see you
I
now.
use because I was still in the Discord call.
Oh, it totally
that'll do it.
was. Your
Yep.
camera was in use.
Yeah.
Yup, that'll do it.
Resolved.
Alrighty. So whenever you guys are ready, you guys can go ahead.
Share my screen here.
Oh, you're sharing?
Yeah, I can if you want. Yeah. Let's see. Where is it? You guys can see that?
You're good.
Yeah.
Cool. This is preliminary design review for Team Too Big to Destroy by Ethan Walker and Joshua Cheng.
Yeah. So to come up with our initial design, we follow the flow of what the rocket will go through. And so we had three basic steps that we was thinking about. So the first is deploying the parachute. And then the second one is correcting the orientation after it landed. And the third is launching the projectile after we push the button. And so focusing on the later two steps, because that's the major challenge, we think we came up with two major designs. And based on that, we make a decision matrix, and then that's how we got to our final design. And the two major difference between the design is basically a spring launcher versus a spinning wheel launcher. And for the spring launcher, we basically want to put the projectile inside a tube, and then inside there will be a spring that pushes the projectile out into the air. For the spinning wheel, we will have a projectile that sits behind the two wheels and then speed up the wheels until it reaches a certain speed, and then have a small piston to push the ball in contact with the spinning wheels to launch it out.
Real quick, do you want to be on the next slide right now?
Oh, right, yeah. Yeah, so this will be how it looks like basically, and yep. And then yeah, it will be shape of payload.
Yeah. So for the shape of payload, that was the other aspect of our proposed design. So we had 3 shapes that we were considering. So the first shape was just a cylindrical shape, and the second shape was just the same cylinder but with a flat bottom, and the third shape was a rectangular shape. And the shapes sort of play into the launcher design as well, because the thought was with a cylindrical shape we could correct the orientation, and then with the cylinder with the flat bottom we could kind of ensure that it would land on that side, and then the rectangular shape we would have a finite amount of sides that we could predict that the launcher would land in. So for example, for a rectangular launcher, maybe we'd have 4, or rectangular shape we would have 4 launchers, versus a cylinder with a flat bottom we would just have 1 launcher. So that's how those sort of played in together. And then just other miscellaneous proposed designs that we had, utilizing an accelerometer to set the launch angle of the tube so that the launcher could be in a set position when it lands, and then we would be able to change it into a launch position. We considered a detachable parachute. We're probably going to decide against this just for safety reasons. It may be a little too complex, but the thought there was that we could ensure that once the lander landed on the ground, that the parachute wouldn't catch any air and sort of flip it upside down or something like that. So that was something that we considered, but just because of safety reasons, we're probably not going to move ahead and do. But the last proposed design was, we were discussing what projectile we're going to use. And so one thought was a disc-shaped projectile, just because it'll roll less than a spherical shaped projectile. We could predict that it's going to land once it hits the ground. The problem with this, though, is that it may not be as stable in the air as a spherically shaped projectile. So that is something that we'll have to look into a little bit more.
Yeah, and in deciding which launcher to use, we used the decision matrix, and here we can see 4 columns. So spring launcher with rail system 1 is the system where we would use with a cylinder with a flat bottom. And then for spring launcher with rail system 4, it would be a system we use with the rectangle shape of payload, because we can only ensure that it will land in one of 4 orientations. So we would need 4 launcher in order to be able to launch in either direction. And yeah, same with the spinning wheels. And so after this setup of comparison, then we went on to consider in a descending order of importance the ease of setup, space efficiency, ease to fine tune, ease to assemble, and the ability to change orientation. And then, like, considering all of the weighting, spring launcher with rail system in a half cylinder with a flat bottom basically is the most optimal design. Spinning wheel was looking pretty promising at first, but because after we do the calculation, it have a very high power requirement, and so it will be very difficult to fit 2 motors into the half cylinder. So it have a very low space efficiency, and basically rule that out from our proposal. And yeah, so this is basically why we chose to go with the spring launcher.
And then for our decision matrix for the shape of the payload, Obviously, we had the cylindrical with flat bottom, cylindrical, and rectangular. And so our wants were that it'd be able to land in a specific orientation that we could predict, and then potentially correct its orientation, and then space efficiency, or just the volume of the shape. And so, for example, the cylindrical with a flat bottom, we'd be able to pretty easily predict what orientation it would land in, versus like a cylindrical shape that would be pretty much impossible to predict. And for the and then for the opposite, cylindrical shape would be easier to change the orientation compared to a cylindrical with a flat bottom or a rectangular shape. And then for space efficiency, because the rocket is going to be in a cylindrical shape, obviously the cylindrical payload would just be able to have the most volume. Because like, for example, with a cylindrical with a flat bottom, you lose the volume where you cut it. And then with a rectangular shape, you lose the volume on all the sides because it's only as big as like the corners can get on a rectangle. And then after weighting and rating all of those shapes, the cylindrical with a flat bottom was the one that came out on top. And after this, we went into some calculations. So I worked on the calculations for the spring launcher. So I started off with energy analysis, and that gave me initial velocities in the X and Y direction. And then I utilized that for the projectile motion analysis, and that gave me a number that I could plug into a spreadsheet for the spring constant. And I left mass, desired compression, and the angle as variables that we could change. Even though we are aiming to have a 200 gram projectile, because that would be the highest scoring, and we're probably going to use a 45-degree launch angle because that's the optimal launch angle. I still wanted to keep those as variables just so we could change those and see what our spring constant would be. So if you look at the top row there, that's the most likely scenario, and that gave us a spring constant of 8.82 about pounds per inch. And that sort of guided us in finding a potential spring that we would use for our launcher.
So for calculating the outputs, it's still the old version. Maybe, Ethan, you need to exit the presentation. Yep. Yeah, so in calculating the power requirement for the spinning wheel, similarly, I started with calculating the initial speed the projectile will need to reach in order to launch to 15 feet, I think. And so after calculating the initial speed, I use a heuristic to calculate. I use a heuristic to decide how long the projectile will be in contact with the spinning wheel, which is half an inch. And so with this heuristic, we basically can calculate the, because we have the kinetic energy and we have the time of contact, we can calculate the power. And so launching at the optimal angle, which is 45 degrees, the motor will, the entire system will require a power output of 1200 watt. And so, yeah, and so we tried finding motors that fit this power output, but then a lot of the times, actually we haven't been able to find a motor that it has a practical size and practical voltage input in order to fit in our system yet, which is why this design is, even though initially we think it will be one of the best one, it's still just not practical for now. And so, yeah.
So after our calculations and decision matrices, we went ahead and just did a simple CAD in SolidWorks just to sort of visualize our ideas and get our ideas across. So as you can see on the left there, the payload in pre-launch position, that would be how it would be coming out of the rocket and while the parachute was still attached, or while it's still in the air. And then we have the cross section there, so you can see the spring in the tube, and there's the section to the right of the tube where the motor would a motor would connect into, and that would allow the tube to raise into the launch position that you can see on the right. And not pictured in this is the rail system that would just compress the spring and allow the projectile to go in.
So with this final design, what's something? So with this final design that we decided on, what's left is to incorporate the accelerometer so that we know that after it landed on the flat bottom, what angle would it be with the ground, and try to adjust the angle of the launching tube to be 45 degrees with the ground. And other than that, we still need to think about how to incorporate batteries and like servo motors in order that we can actively adjust the tube and change the angle of the launcher. And so, yeah, that's pretty much how far we've got with the final proposed design. And yep, thank you.
Much. Stop sharing there.
All right, thank you guys. I'll start off with a quick question. So you guys mentioned the accelerometer a couple times. So I just want to make sure I am clear on where you guys are going with that. So you're trying to judge what angle you are, like if you're on a hill or something like that, right?
Exactly, yeah. Just because we don't know where we would potentially land.
And then you'd be adjusting the shooter for that to be 40, like a certain angle off. Okay.
Yeah. Depending on whatever we calculate. And
if you're like pointing up slope or down slope or like on a side, it might roll or, okay, cool. Well, actually, I don't know if you'd be able to do much about rolling, but up or down, yes.
The rolling's probably not going to be predictable, so you're going to be on some terrain.
Yeah. Well, and if you use a disc, maybe, which actually that was also a question someone had, Nathan, if you wanted to ask that.
Yeah, my question was, is there an easy way to spin the disc-shaped projectile, like with the spring launcher, if that's what you're decided to go with?
Yeah, that's another problem with the disc shape, is that if we were to utilize it with the spring launcher, it would just sort of be sitting against the spring, and you wouldn't really be spinning it like as you were saying, like a frisbee. So it'd potentially be less stable in the air, and would end up possibly rolling anyway.
Yes, maybe it's possible to like make a, like in the rail system, make like a gear so that when you pull it, it also spin it so that when it launches. But like that's not something we have really gone in depth in yet.
Yeah, actually, I'm going to jump off that point. You guys have mentioned a rail system a couple times, and I'm not entirely sure that I'm following what you're saying. Is that to pull back the spring?
Yeah, exactly. And you can talk, Josh.
Yeah, so like hold back the spring and also to fix the projectile so that it will launch in a set path. So it wouldn't wiggle or like anything like that.
Okay, so it's like a centering and like make sure that it like follows the straight linear punch. Okay. So would the projectile actually be like slotted into that rail kind of thing? Or is that just based on whatever pusher plate you have, that geometry would be locked into the rail and then you'd be constrained within that pusher plate?
Yeah, so it will be, well, so with the rail system, ideally it will lock into the center. So it would be limiting the, yeah, so let's say the tube is like oriented XYZ, it will limit the XY movement and only allow Z movement.
Gotcha.
So would it be like a ball bearing carriage to limit friction? So like it would slide along the rail really fast and leave, that kind of thing, or is it? Have you considered having the projectile be a linear carriage?
Having? Like,
what's up?
Oh wait, sorry, I didn't catch.
Like if you've got your rail here, and you have your projectile be a linear carriage that rides on the rail, and then the whole thing just leaves.
I'm saying like shoot like a linear bearing.
Yeah. Yeah, exactly. Potentially a simple way to do it. But
Technically, that would work.
That'd be kind of cool.
Yeah, the rail system is something that we haven't necessarily thought about too much. And I think another aspect of the rail system was just the idea that it would be able to also like incorporate some sort of like safety pin so that spring would launch just whenever. And that would be something that we would somehow incorporate and be able to like press the button and then that would be released.
you want to make sure that it doesn't impale your hand when you remove the safety pin. I think it would be very easy to make such a system in such a way that, you know, if it failed, it would impale your hand.
Yeah.
Don't hurt yourselves, please.
No, I mean that is going to be an easy mechanism to restrain, as you say.
Yeah, just make sure if your mechanism fails and you're against your safety pin, you can safely remove the pin.
Because I mean, if this is, you know, fully stretched, I imagine that this thing might have, you know, 60 pounds of spring force on it or something like that.
Yeah.
Yeah. So
yeah,
dangerous.
And going off that, do you have any ideas about the release mechanism that's going to let the spring go?
60 pounds is a lot to hold on to and then let go of without, you know, the friction being too much.
As of right now, that's not necessarily something that we've thought about too much, just because we were focused on the launcher and the shape and everything like that, and getting like the general ideas down. But that's definitely something we'll look into as we move forward.
It's totally doable.
Yeah. Also, as a side note, good job answering that question, despite the fact that like you didn't know. That's totally fine, especially in the PDR. Like you didn't try to like make up something on the spot. Like, you're good. Like it's okay to say you don't know.
It's a very solvable problem.
Yes.
I have a question about a completely different thing. So what happens if you land, you want to go with the cylindrical with the flat bottom shape, but what happens if that lands upside down in, say, tall grass? It'll probably be pretty well balanced. You might not take too much force from the grass to hold it upright, upside down.
Yeah, I think so like it would have to be something that's like an external device outside the tube. But yeah, we really haven't gone into much depth for this yet. Yeah, but we basically brainstorm it could be a small circle that like kind of flip it, or we could like just put spring and then when it touch down, it release. And so if it's in the correct orientation, it would just release into the air. But if not, then it will pushes the entire payload. But yeah, I don't think, it might be a dangerous system. We haven't thought too much about it. And to push the payload, the spring probably will be pretty strong.
Yeah, exactly. The one thing I will note is we have some past experience with trying to flip things over like this. Make sure you don't underestimate how much, you know, spring force or motor force, torque, whatever your mechanism ends up being if you end up going that route. Make sure you consider like the effects of being on a hill or like some like bumpy, or as Adam mentioned, like tall grass. We're not just trying to be a pain and be like, oh, you have to account for every possible scenario. Like these launch fields are cornfields by and large that will like have bumps and it's dirt and like maybe some mud or something. So make sure that you like consider that if you end up going that route. Also, an interesting thought is you might be able, real quick, you might be able to use the lift of the shooter to like at least roll it over a little bit. I don't think it would bring you all the way, but if you landed like perfectly upside down, I think that because that's round, that if you extended that up, that it wouldn't be able to balance like on that, and it would at least roll to a side. Yeah, so you might be able to assume that you're at least on one side or the other.
You could probably also get the CG low enough that it's like one of those things that I don't know what they're called, but yeah, so it'll you can tilt it pretty. If you get the CG low enough, you can tilt it pretty far, and it'll still try to flop back to the same orientation.
Yeah.
What's the thing I'm thinking of? It's like a hemisphere with like the weight all the way in the bottom, and it just like wobbles, and you put something on top of it.
I mean, I don't know what the technical term is. I'm familiar with the kids' toy, a Weeble.
Yeah, me too.
That's kind of the opposite of what they're trying to do, though, right? They really need the flat side to be the heavy side.
Yeah.
Yeah.
But
now all I
gets,
can think of is
but
Weebles wobble, but they don't fall down. It's
I
like
know, me too.
ingrained.
You can still play with the CG a little bit, right? Be
Yeah,
careful
I mean, you
your
can put it
batteries,
as low as you can, but you're not going to be able to get it to.
No,
you're going to have a hard time getting it to actually flip over by putting weight on the flat side, I think.
Unless it extends most of the way back around, I think.
Yeah, or like if the flat side's
flat
small,
side.
kind of thing. Yeah, if the flat side's small, then you could get it to work, maybe. Which, I mean, that's an idea. My other question.
Yeah.
This is
Wait,
unrelated.
We do have
Andy
to...
first. Hang on.
Are we done?
Do you guys see what
Nope,
we're saying?
you're good.
Because you're at almost 180 degrees with the flat side. If it's on its side, the center of mass will be like over here somewhere. So even if it's most of the way over, it's actually going to want to tend back to the bottom. If you extend that most of the way around the circle, your center of mass is over here. You're past that center line, so it will roll onto the flat side.
Yeah, exactly. That's actually what we have right now. Is that it's a little past the directly cut in half, so it's not actually directly cut in half. So the idea would be that it would hopefully fall on that side, and that we can ensure to a decent probability that it's going to land on that side.
Except for the mud. Yeah. But yeah, okay, that makes sense.
We do have horror stories of like boots sinking to ankle depth into the mud.
But yeah, I mean that's at least a place to start. And obviously, it's going to be very difficult to make your thing resilient in any scenario. But
like it's not going to be bulletproof. We get it. Like we want to give you guys as high of a probability possible of it working, because it's fun when stuff works.
but it is reasonable to be like, well, if we land on say a corn stalk, that's it. We can't do it.
Yep.
So, unrelated question though. We're almost out of time. Flywheel, why 2 specifically?
Flywheel. So it could be. I feel like if one. Well, yeah. This is just what I think. I haven't really calculated it, but I feel like if we just use one, then one wheel will be a passive wheel, or like even if we don't use one, if we entirely just have one, then it would kind of not go strict, but go somewhere that maybe less than once. Yeah, deviated from the straight line, which would be hard to calculate, which is what I thought about when I decided, maybe 2 is better. But yeah, I don't know if it makes sense. I don't have much experience designing spinning wheel launcher, but
yeah, I mean it's true. You'll put a bunch of either top spin or backspin, depending on how you do it, on the projectile if you only use one wheel.
Yeah, backspin could actually help you. It could give you a little bit more range.
But as he says, it'll become more difficult to calculate your trajectory. It'll have to be all just empirical data, essentially.
Oftentimes with flywheel shooters, it is empirical. You can use
Regardless
theoretical
of how you
calcs.
do it is the thing.
Yeah, you can use theoretical calcs to get you a ballpark to start, but at the end of the day, you got to test it.
Yeah. Also, if you only
that might not be a pro of the 2 flywheels. That's the thing. I mean, that's gonna be trial and error too, probably.
Yeah, that's fair. Yeah.
Yes.
If you only have one wheel, I think it has to spin twice as fast, right?
Yeah.
Yep.
But the force it imparts, average force, I guess, could be less, right?
Yep. And you can impart it over a larger distance.
Yes.
Yeah.
So there are pros and cons there, potentially.
All right.
We're
I'd
out
love
of
to keep
time,
talking to you
aren't
guys,
we?
but we are supposed to be done by 2 minutes with even the next group. So, yeah, I'm going to have to let you guys go. But thank you again for presenting. You guys are doing a good job. Over the next couple of days, we will compile the notes and questions and stuff that we've discussed, and we will send them to you guys. We're doing that for all the groups. And I look forward to seeing what you guys come up with in the spring.
Thank you so much.
All right. Have a good break, guys.
Yep.
All right. We don't really have time to talk much.
That's okay. I think we can.
I think, yeah, I'm just going to let them all in.
We can just debrief at the end.
Yeah. Hi, guys. Can you hear us? I am terribly sorry that we are like many, many minutes late for you. Yeah, I should have foreseen this, but I didn't really have a choice.
Yeah.
So, do you guys have a link to your presentation that I can snag?
I will add it to the doc, Scott.
Thank you. Alrighty. So one of you guys, if you can share screens, that would be good. And whenever you're ready, you guys can take it away.
Guess I can share my screen. All right. See our screen?
Not yet.
Oh,
Oh, it's thinking about it.
See it now?
Yep. And if you hit present, that would be top right.
Oh.
There you go.
All right. Guys ready?
Yep, I'm good.
Ready whenever you guys are.
All right. So we are the Cherry Tart Lads. This is Nicholas Kotaj, Bhavesh Malapathy, and Mata, and myself, Mata Susie Dallas.
All right. So to overview, this is a project from Intro to Rocketry Mechatronics, as you would have known. And we're designing a payload system that essentially qualifies a task, which in this case is shooting a projectile around 15 feet away from the landing place of the payload. And one important aspect of this project is to work with the systems given by the avionics groups and design our own projectile to fit with it. Just to be sure that our project is not like 100% done, but we are pretty sure with an idea for how we are going to launch. And for now, we are just coming up with more efficient designs for our launching mechanism and the kind of case that we're going to build and the materials, etc. So in general, we're going to go over the challenge, the design, why did we choose to do that, and our future plans. So yeah, most of these are known already, that diameter should be a bit lesser than like 3.8 inches. The length should be lesser than 8 inches. The weight should be lesser than 2 kilos, and no hydraulics, no pneumatics. Just that.
So we had considered two methods of launching the projectile. One was like a puncher mechanism where we would kind of punch the projectile out of a barrel, and the other one was like a flywheel mechanism, kind of like a sling, where we would spin around projectile and then release it at the optimal point for it to go flying. So we did this design matrix to decide between the two. And our three main factors were the simplicity, the cost, and how consistent we could launch it, and also the energy efficiency kind of factors into the simplicity a little bit. So where we decided on the puncher mechanism, which you could see in the total, the puncher mechanism had more. And it really reigned supreme in our three main categories, because we decided that would be way simpler than the flywheel, because with the flywheel you'd have to release it at a certain point, and you could totally get that off, and it would go different directions. It would be, and that also affects the consistency, because we wouldn't be sure. We'd have to be pretty much perfect every single time to predict whether or not it will go 15 feet. And cost, I mean, they were both pretty strong with cost, but we thought that since the puncher was simpler, it would also be cheaper. And also it needs less energy, because like the motor is kind of like the main part of the flywheel design, because it needs to spin around the flywheel. And we thought that motor wouldn't be as integral to our puncher design. So this was kind of like the initial design for the puncher, where initially it was a motor would compress a spring, kind of like pull on a cord from like the launching platform, compress a spring, which we would have a catch that would keep it compressed, and then the motor would spin the opposite direction to kind of release the tension of the cord. And then once the device is triggered, the catch would release and the projectile would launch. And we were discussing with the mentors and amongst ourselves, and we decided that we didn't even need the motor. We could just pre-compress the spring, which, you know, it adds more simplicity and removes a moving part.
Okay, so the design process involving the landing portion, or the landing function of our projectile was discussed to a certain extent. So initially we had it so that we had a really complex system of a crumple zone kind of situation where you have a whole bunch of legs that would break easily underneath the payload once it lands, so that it could cushion the fall in a way. But we realized this was more of a liability than anything else, so we decided to simplify the design more by reducing the amount of legs, and the legs that would be used would have two different functions. One would be one function, which is to be leaned on once the payload lands on the ground. And an additional design factor that we took into consideration was making the bottom of the payload overall simpler design by having some sort of rubberized finish to it, or a rounded off finish. Some features and designs that we had, these were more of the calculations and some future designs that we had. So there was a lot of math involved in just in the simple 15-foot minimum goal. Additionally, we figured out what the minimum velocity that the projectile exiting out of the payload has to be. We eventually figured out it was about 6.7 meters per second at a 45-degree angle, and this is the most ideal situation where there's no drag or any of the sort. Additionally, we calculated the acceleration that the projectile needed to experience inside the payload to go from rest to the set velocity that we agreed on. So if it's traveling from rest to the velocity in 8 inches, which is the maximum height of the payload, it would be about 110 meters per second squared. However, I did some quick calculations for 4 inches, and it was about double, so 220 meters per second squared. So I'll have to figure that out for spring or future spring considerations to buy. And an accelerometer could also be potentially used to set the angle of the payload to a ideal angle if the payload angle is not even with the ground. And so, yeah, again, there was a crumple zone that we talked about that we eliminated, and the to need. Oh yeah, and I'm sorry, and to somehow vision the electronics in some way. That was also something we considered. Future plans were to use maybe a blue tube for the external shell of the payload. We also considered creating a 3D printed shell of some sort. Additionally, this is the SolidWorks model that we came up with for the linear motion system designed to shoot the projectile. You have any questions?
One second. Thank you guys. Good job. Yeah. Sorry, I was just sending out messages and making sure everyone didn't leave. Good job, though.
Yeah, I will fall into the trap and, well, actually, sorry, misread that. Rules, I can't ask about that. Where the name came from.
What?
Not allowed to ask. This question is the only thing.
Oh.
It's proprietary.
On a need-to-know basis.
Yeah, not even all group members know, I don't think. I mean,
Wow.
maybe they all know like part of the
I mean, I know part of the origin.
But nobody
I'm not
can
sure.
know all of it.
It's like the Coke recipe.
Vash is probably the only one who could fully explain it.
Anyway, so one thing I just want to check in on is I know that I discussed the legs with some of you last week, and so not all the reviewers here were privy to that conversation. So I apologize if this goes like slightly over your head, and we can also explain a little bit of this. But I'm just kind of curious where we're at with those. As a quick summary, there was, at least as of last week, there was a plan to have multiple sets of legs. There were like the landing legs that were supposed to like dampen and cushion the fall, and then there were the legs that made sure that, or that like tilted you the right way, so like they can, it's upright but then tilted, and like that sets those, or that sets that. So just kind of, and we were talking about like materials and all this sort of stuff. I just didn't know if any progress had been made on that. Doesn't have to have been, but if there is, I'd love to hear about it.
Yeah, I was thinking about the design process for that as well, actually, over the weekend, and I was thinking about trying to eliminate those legs and somehow coming up with some design where the bottom of the payload would be rubberized or have some sort of other type of cushioning effect, or just to absorb the impact from the 10 or 15 foot per second terminal velocity that it should be experiencing. And I was thinking just to have those four main legs, like you said, be already like propped up before the payload lands, so that once it lands, it doesn't need to be necessarily upright to be ready to shoot a projectile. Does that make sense?
Okay, that's a cool
yeah.
idea.
So you've got four. Oh, I don't know. You got sort of four legs sticking out, right? So that any orientation it lands in, it ends up at the same, sticking up from the horizontal at the same angle, right? That's the idea.
Yeah, that's a cool idea.
Yeah.
That actually answers one of the comments I was going to make. I was going to say landing on the end of the payload sounds like it'd be difficult. If it's a 4-inch diameter and 8 inches long, that's probably about the aspect ratio of like a can of soup. If you took a can of soup to like a grass field and dropped it a bunch of times from a couple of feet, it probably wouldn't land on its bottom too many times.
Especially if you got a parachute carrying it over.
Yeah.
Yeah, but I think the legs help to mitigate a lot of that. I think they're pretty creative. I'm still very curious how you're going to manage to package those, but I think it's possible. It's just going to be tight.
Well, if you were able to make your launcher teeny, you could just make part of your payload be 3.9 inches in diameter, and the rest of it be like, I don't know, 1.5 inches in diameter. I don't know how you'd ever manage that, but that would essentially eliminate your
give you
the
room.
need for
Yeah.
deployed legs.
You wouldn't even need legs at that point. You could just kind
That's
of build
what
it
I
into
mean.
the external
It would
geometry.
just automatically tilt itself no matter how it lands. That would be the point there. That's why that's the only reason why you would limit yourself to that kind of space, I think. But
Yeah, one thing that Andy was noting was regarding Bluetooth, which is a good point I didn't think of. See, Bluetooth is sold intending for you to use it as a rocket component, which doesn't mean you can't use it here. But it's worth noting that you can buy like 4-inch diameter outer tube, body tube, or you can buy 4-inch coupler for a 4-inch rocket, which is slightly smaller. And these are components we will be using for these rockets. So if you want to buy Bluetooth that's a size down from that, it's not like you can just buy one that's like 3.75 inch OD. Like there's standard rocket sizes, and there's 4-inch rockets, and then there's like 3-inch rockets. So you'd be limited to a significant step down.
Yeah.
They don't
What
just
is
sell
it
it in
for?
all ODs.
4-inch, 75, 54.
Yeah.
Both of those are millimeters.
Yeah. Yeah, 54
75 is 3 inches. 98 is
54
4
is
inches, and there's nothing really in between, I don't think.
Yeah.
So you can get, like coupler and main tube, and the coupler fits inside the main tube, but I mean, you can't get anything. Like this is a tight fit, right?
Damn, Andy, where were you the other night when I was trying to explain coupler?
I'm sorry.
You just have literally every visual you ever need on next to you. You whenever you bring something up, you're just like, oh, here, I have it.
I don't know. I think
it's
awesome. It's easy when you're the one who brings it up, right?
For sure.
You bring up the
So
stuff
that's how you do it.
Yeah, well, just to mention your concern about that Bluetooth, that's one of the options we were considering. Another thing was to use a 3D printed shell of some sort. That way we can design it any way we wanted at any radius or diameter. So, yeah.
That's a pretty big print, but if you have a good reason, it could probably be done. Do you guys have a printer?
No, but I have one.
Yeah, we all do. That's fine.
It's just too bad that your mentor doesn't know anything about additive manufacturing.
Yeah.
Do you want to use the Phylic printers?
No.
Don't try to use the file.
They'll be worse.
Wait. Okay, I want to make something very clear. We were joking around. If you need something printed, we will get it printed.
and our printers are far better than theirs.
Yes, I don't care what they say. I'm telling you, we will beat them.
I had to print a part the other day that was supposed to take 10 minutes, and I got it 3 hours later. They lied to me.
Yeah, don't use the library. Don't use Phylic. Don't just talk to us if you need parts printed. Even for not this club. If you need stuff printed, let me know, and I'll charge you filament costs. That's it. I don't care. Don't deal with that. Within reason.
To be clear, if
my
it's
cues
for this,
do exist.
For this project, you're not being.
Oh yeah, you
charged
will not pay
cost.
anything. It's for this project. If it's a completely personal thing that has nothing to do with Arrow and you just want it printed, then I might charge you filament costs, but that's it.
I won't. Come to me, unless it's Nylon X. Yeah,
that depends.
Or
if
at least for the
if it's PLA, I don't care.
At least for the first 2 jobs, if you tell your friends, I think we can get.
Andy is starting a
here.
business. Okay, we should get back on track. There are people waiting.
Yep.
Are we not the last group?
Yes, you are.
Oh,
yeah, but we're going back into the main call at the end of this for the recap.
It won't be long, but I just want to talk to you. I know some people have already left, but I'm hoping to just touch base with you guys before you go because this is the last meeting of the semester. So, okay, I don't actually have any other questions right now. That's partially because I talked to you guys a ton last week, so we had a lot of. I asked a lot of my questions already. If someone else has any questions, feel free to ask now, but if not,
it's not mine, but there's a question about the flywheel that I'm interested in. I don't understand it though.
Yeah, that was my question. You guys talked about some kind of sling, like you got a thing and you're swinging it around like this, and then you let go of it or something like that? Is that what you meant by flywheel?
I think my team was a little bit, our team was a little bit confused about just maybe what the design of what the fly was about. So originally, one of the designs, this was like way back before we started consider like for real, like what the design should be. We were thinking about doing like a slingshot kind of effect where you spin like a swing around where the projectile sits inside the swing. This flywheel on the design matrix was having two discs spin really rapidly and having the projectile shoot off from those discs. So
makes sense. Yeah.
Yeah.
Okay. And was there a reason you considered 2 discs over 1 disc?
No reason. It was a loose idea, and to be really honest with you, it was I considered the flywheel design just because you guys thought it was cool.
Fair enough. Yeah. So you considered that it was too difficult, particularly considering that it's difficult to prototype things right now.
Yeah, I mean, I'd be more than happy to do it with you guys, but yeah.
No, fair enough.
It was a bit too difficult to get right.
Pick your own designs. Just because we think something's cool doesn't make it the right idea.
It's cool, but given the extent to which it's hard to prototype anything right now, and the extent to which it's impossible to figure out what's going to happen with the flywheel without prototyping,
yes,
there's something to be said for going with a puncher where you can actually calculate, potential energy of the spring, and a reasonable amount of it will probably get transferred to your projectile, or at least you can calculate how much will.
Yeah, it's funny how we didn't expect that to necessarily be a design factor, but it is, and you guys made a good choice with regards to that.
Absolutely.
Yeah, and just limited time and stuff. I mean, you can't devote every waking hour to no, yeah, I mean, you can't. You've got classes, so you can't devote every waking hour to this. So good choice.
Yep, absolutely. All right, I think that's all I had. If no one else has any closing comments, I think that we're probably all set here. Thank you guys for presenting to us. You guys did some great work. I'm excited to see what you guys come up with in the spring. And we are meeting in Intro Mech General like now, as soon as it ends. So I will see you guys in a sec.
All right.
Cool. All right.
Thanks,
Adam, yeah, no problem. Adam, if you want to come, you can. If you don't want to come, you don't have to. This is not an integral part for you, so that's your call.
All right. I'll probably run away. And then
okay.
Should the 3 of us regroup and discuss later?
Yes. Ultimately, yes. I don't know if that makes sense to. Well, I would really probably rather that not happen tonight because I do have a lot of stuff to do.
Yeah, same. I wouldn't mind briefly discussing the last 2 groups just because we didn't actually get to.
Yeah, that's fine. So how about that? So we'll do that. Let me go close out with them. And
yeah,
then,
let's just do that in Corona Camp. That way, we'll jump in.
We'll be alone.
Yeah.
Okay, sounds good.
That's good.
Alrighty. Thanks, guys. Appreciate it.